In this video, we're quickly modifying Gauss's law to work in the context of a dielectric, and this is more of a motivation than a proof. We're actually just going to look at this specific context of a parallel plate capacitor with a dielectric sandwiched between the conductive plates, and we're really just focused on the interface between the upper plate and the dielectric material. So once we've successfully modified Gauss's law to work with dielectrics, we're going to apply that to the spherical capacitor with a dielectric between the two plates of the spherical capacitor. So we're going to completely solve that spherical capacitor, including electric field, potential difference, capacitance, and energy stored in the capacitor. So just to point out the details of our parallel plate capacitor for this derivation, our upper plate is the positive plate, and inside that conductive material, I have an electric field of 0, but it has a surface charge on it that I labeled over here on the right-hand side, and we called that plus sigma. Remember, that's an area charge density measured in coulombs per square meter. And of course, the electric field between the plates points from the positive plate to the negative plate, and we just called that E. But that space is filled with a dielectric material with a dielectric constant that we called kappa. And remember, that dielectric material is polarized so that I have a negative induced surface charge on its upper surface and a positive induced charge on its lower surface. So now we're just going to apply Gauss's law at the upper interface between the conductor and the insulating material. So there's a Gaussian pillbox centered on that interface. And we apply Gauss's law to this thing. So we have our flux integral of the electric field over the area of that Gaussian surface is equal to the enclosed charge divided by epsilon 0. Okay, next, when we're looking at the enclosed charge in this Gaussian pillbox, all of that is contained at the interface between the conductor and the dielectric. So the surface of the conductor has this area charge density of sigma. If I multiply that by A, I get the enclosed free charge on the conductor. So we use that phrase free charge for charge on a conductor. At the same time, I have some amount of induced negative charge on the surface of the dielectric. So again, I can get the total charge due to that induced component by taking the density times the area. So this first piece, sigma times A, that's the enclosed free charge. And that second piece, sigma induced times A, with a minus sign out in front, that's our enclosed induced negative charge inside the Gaussian pillbox. But now we remember that the induced surface charge density on the surface of a dielectric can be written in terms of the surface charge density on the conductive plate. And this relationship was derived in a previous video where we really got into the details of everything happening in the parallel plate capacitor with a dielectric. So here's how it turns out. And in this line, I've also factored out the A out in front, but I replaced my induced surface charge density with a sigma times 1 minus 1 over kappa, where kappa is the dielectric constant. So notice that we're going to get a nice cancellation here, where a sigma cancels right there and right there after we distribute the negative sigma into those parentheses. What remains in those big parentheses is just sigma over kappa. And that allows us to simplify the right-hand side of Gauss's law to just A times sigma over kappa epsilon 0. Now in our final step, I'm going to do a couple things. I'm going to multiply both sides by kappa, and that's going to put a factor of kappa, the dielectric constant, over on the left-hand side inside this integral. The other thing I'm going to do is replace A times sigma with the enclosed free charge. So that's an area charge density on the conductor multiplied by area, which gives us the charge on the conductor enclosed in the Gaussian surface. And again, we use the phrase free charge for charge on a conductor. So putting it all together, this is our modified version of Gauss's law when there's a dielectric present. And the way to look at this is that we're calculating the flux of kappa E on the left-hand side. And then the remarkable thing about the right-hand side is only the free enclosed charge matters. The induced enclosed charge doesn't matter at all for getting this calculation done. Okay, so now we know how Gauss's law works in the presence of a dielectric, and now we're ready to apply this to the spherical capacitor. So here's our classic spherical capacitor. I have an inner conductive shell with a radius of A and an outer conductive shell with a radius of B. What's different this time is that we filled all the space between those plates with a dielectric material that has a dielectric constant of kappa. Now we still have an electric field that we call E pointing from the inner plate to the outer plate. And we've already placed charges of plus and minus Q on the two plates. So I have a positive charge on the middle plate, a negative charge on the plate that surrounds it. That's why the electric field is pointing from the center out. And what we're going to do here is more or less answer every possible question we can think of about this spherical capacitor. So we're going to start by finding the electric field between the plates. Then we find the potential difference between the plates. And we do that by taking a path integral of electric field. So we're using our previous answer. Then we get the capacitance, which is found by taking the ratio of charge to potential difference. And then we get the total energy stored in the capacitor by using the formula 1/2 Q times V. So that's just a quick modification of 1/2 CV squared, where we replace C with Q over V and simplify it a little. It just turns out to be easier to do it this way. And then finally, E is a really interesting part of the problem. We're going to verify the total energy stored in this capacitor by actually integrating over the electric field energy density between the plates. So the electric field energy density, if you recall, is proportional to the square of the electric field. Since that's dropping off with distance from the center, our electric field energy density is constantly changing, and this is why we need to use an integral to add up all of the energy contributions. So with any luck, the answers to parts D and E will agree with each other, and let's get started. So we want to find the electric field between the plates, and what we're going to use for this is our new version of Gauss's law. So I need to visualize a Gaussian surface that shares the symmetry of the charge distribution, and that's just a concentric spherical shell. So there's our Gaussian surface. It has a radius of little r. And we write down our modified version of Gauss's law. So I have the integral of kappa E dotted into dA is equal to the free charge enclosed. So this is really nice. We don't have to worry about the induced surface charge on the dielectric. All I care about is the free charge enclosed, which is plus Q. And perhaps I should point out before we continue, I'm not even calculating the field inside the inner shell or outside the outer shell. I can tell immediately those fields are going to be zero. The interesting place to us is the region between the two plates. So all the usual things occur here. I realize that E is perpendicular to the Gaussian surface at every point. In other words, parallel to the area increment vectors. So the dot product is trivial. At the same time, the field magnitude must be constant over the surface just by symmetry. So I can factor the electric field out of the integral. Now kappa is also a constant, so I'm going to factor out a K times E, where E is the electric field magnitude. This leaves me with the integral of dA over that spherical Gaussian surface, and on the right-hand side, still just Q divided by epsilon 0. Now the integral of dA is just the surface area of that spherical shell, and that's just an old formula from geometry, 4 pi r squared. And I can solve for the electric field magnitude as a function of r. So I get Q divided by 4 pi kappa epsilon 0 times r squared. And remember, we had a name for kappa times epsilon 0. We just used the symbol epsilon for that, and that's called the permittivity of the dielectric material. And basically the whole reason that we defined that is to make a lot of our formulas analogous to what we saw in a vacuum. So it works here as well. I end up with an electric field of just Q over 4 pi epsilon r squared, where epsilon is the permittivity of the material. And that looks just like the electric field between the plates of a spherical capacitor in vacuum, except in vacuum, it was an epsilon 0 there instead of an epsilon. So there's our first result. E is equal to Q over 4 pi epsilon r squared. Next, we're going to find the potential difference between the plates by using this electric field. So the first thing we have to do is visualize a path between the plates so we can do an electric field path integral. So there's a radial path between the plates. We call the starting point 1, the finishing point 2, and we know the potential difference V1 minus V2 is given by the path integral of E dotted into dL, where dL is a little path increment along that path. Well, we arrange the path radially. So saying dL is the same thing as saying dr, and just for completeness, we'll put the little 1 and 2 on here, indicating the starting and finishing points of our path. So we realize the dot product is trivial again, because I have E pointing exactly in the same direction as the path increments. E points radially, and my little path increments are also radial. So I get just the product of the magnitudes of E and dr along that path. And then we're integrating as r goes from A to B. Okay, so now we can sub in our electric field magnitude of Q over 4 pi epsilon r squared. And the Q over 4 pi epsilon, those are all constants, so I'm going to move them in front of the integral. And then I have the integral from A to B of just 1 over r squared dr. But 1 over r squared is r to the negative 2, and that integrates to negative 1 over r. Now when I sub in the b for the upper term, I get a negative term, that's negative 1 over b. And then when I sub in the a, I get a positive term because I'm subtracting that result. So I'm just going to reverse the direction of those just to clean up the algebra a little more efficiently. So I have the q over 4 pi epsilon out in front, and then this is multiplied by the quantity 1 over a minus 1 over b. I do want to point out here that I felt inclined mentally to at least check that this has the correct sign. We're expecting the potential at point 1 to be higher than the potential at point 2 because point 1 is over there with all the positive charge. So I did a quick mental check that 1 over a minus 1 over b is actually a positive number, and that works out because a is smaller than b. So when I divide 1 by a, I get a larger number than when I divide 1 by b. Now the final step here is to get a common denominator. So I multiply the first fraction by b over b and the second one by a over a, and I take the difference between them. So I end up with q times b minus a. Again, that's positive because b is bigger than a, over 4 pi epsilon a times b. So we've got the potential difference between the plates, and now we're ready to compute the capacitance. So remember, this is the standard strategy for computing the capacitance of any plate arrangement. I put charges of plus or minus q on the plates, I find the potential difference between them, and then I use the definition of capacitance, C equals q over v. So we just found v. All I have to do is take q times the reciprocal of that, which is going to be 4 pi epsilon ab over q times the quantity b minus a, and the q's are going to cancel out. And it turns out our capacitance is 4 pi epsilon ab divided by b minus a. So now we're ready to compute the total energy stored in this capacitor. And the first method that we're going to use is definitely the easiest method, but it's a little abstract. Remember the energy stored on a capacitor, the fundamental formula for that is 1/2 CV squared, but I just replaced the C with a Q over V. That's the definition of capacitance. We canceled one factor of V and we got 1/2 Q times V, which is going to be the easiest thing to use here. So this will be our easiest way of getting the total energy, but then we're going to follow it up with a more insightful method by actually integrating the energy density. So we take 1/2 times Q times V, and we already have V written down. That was Q times B minus A over 4 pi epsilon A times B. So not much to do here in terms of the algebra. I end up with a Q squared times B minus A divided by 8 pi epsilon AB. So we've got the total energy stored in the capacitor. And again, I think we can get a little more insight into how this is actually happening by integrating the energy density. So recall in a previous video, we derived an expression for the electric field energy density in the presence of a dielectric, and that was 1/2 epsilon times E squared, where again, that epsilon is the permittivity of the dielectric material. Well, because E is dropping off like 1 over R squared, that energy density is getting weaker and weaker as we go from the surface of the inner shell to the surface of the outer shell. So we can't just take this energy density and multiply by the total volume between the shells because it's continuously changing. What we have to do is break this volume into nested spherical shells. And now inside the volume of a shell wall, we're at one well-defined value of radius that we call little r, and we can take the volume contained in that shell wall and multiply it by the energy density at that specific value of r to get the energy contribution to the total. And I accidentally lost our energy density here. That was 1/2 epsilon E squared. And what I'm saying here is a contribution to the total potential energy stored in this thing. So I'm going to use a du for that. It's given by the energy density at that specific value of r. So I'm going to call that U of r, then multiplied by the volume of that shell wall. All right, so the energy density as a function of r, that's 1/2 epsilon times our electric field magnitude squared. So my electric field magnitude is Q over 4 pi epsilon r squared, and I need to square that guy. And then my dV, that's the volume contained in the thin shell wall. That's given by surface area times thickness. So that's going to be a 4 pi r squared times the thickness of dr, just an infinitesimal increment in the radial direction. So now we start to clean things up, and I have a 1/2 epsilon times Q squared. And then when I square this denominator, it gives me a 4 pi all squared, but I can cancel one of those with the 4 pi sitting here in the numerator. So I get 1/4 pi left over in the denominator. I have an epsilon squared down there as well. And then I end up with an r to the 4th down there when I square the electric field, but I can cancel 2 of those with the r squared in the numerator. So that gives me an r squared. And then we have our little differential dr. So now the total potential energy is found by just summing up all the contributions to the potential energy. So it's the integral of the du's. Oh, and before I put this in the integral, I'll go ahead and cancel one of these epsilons, and we're going to pull all the constants out in front. So I have a q squared over 8 pi epsilon. And then I have just the integral of 1 over r squared dr, and we're adding up all of these energy contributions as r goes from little a to little b. So again, when I integrate 1 over r squared, I end up with a negative 1 over r. And I do the same trick when I sub in the upper and lower limits, and I get the same thing I got before, 1 over a minus 1 over b. And I'm going to get a common denominator there. And so this fraction subtraction in here simplifies to b minus a over ab. And I end up with q squared times b minus a over 8 pi epsilon ab. So of course what we're checking here is that the total energy stored in this thing is going to be the same no matter how we calculated it. And remember, this first one was found by using total energy in a capacitor as 1/2 q times v. But that's a little bit on the abstract side. You could say the second way we computed it, which was by using the energy density, 1/2 epsilon e squared, is a little more direct. So we're a little closer to saying where the energy is actually stored, which is in the electric field between those plates. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.